welcome. Oh, sounds like I'm live. Some reason studio tells me I'm not, but okay, that's good. I'll start like that as long as it's working. It's all good. I'll sort it later. My first live stream on this channel. Hello and welcome. And I hope you can hear me and see me. I do in my test, so it should be fine. Great. So we start today's live stream. I know it's a little bit unpredictable. Unpredicted. I didn't plan to do it tonight, and I didn't know what time, so I just decided I will start it, and then you can see it in recording, and then later I can give you a better in advance notice about my live streams. So why live stream? I noticed that I want to spend some time and talk about some scientific papers on my channel, and I already did just talk about a couple papers, but it takes so long time for me to record it, then edit it, and then post it. So I decided if I will not do it live, I will never do it. So I decided to try this live stream. And I hope you like this idea. And here we cannot just talk about the papers we discuss, but also address some other questions, which I have a lot through my years of having this channel, but I never have time to respond. And actually, I don't have much time also to do other videos because they're very time consuming, my shorter science videos. So if I put sometimes these live streams, it will a little bit kind of make more activity on my channel, and I hope you will appreciate it. So today is the first live stream. I don't know how long we're going to take, so we just go along, and later I will leave this video on for you to watch. If you want to, you can just listen it like a podcast, and I will cut away the sections which will be specifically about the paper and put it as the video on my channel. So welcome to my channel. Yeah, and actually I will put the time codes as well on this live stream later if I'm able to do it on YouTube. I never done it before. I think I did before, so I will do it. So you can go and see in particular sections if you don't want to listen everything, all my mumbling throughout. So for those who are new or never been on my channel, I talk here about some science things, science in particular, earth science, a little bit of space and cosmos, because this topic particularly interests me. And also I talk about ecology, environment. I consider it's part of the earth science, and because I had some experience back in the day in ecology, or how it's called, earth science now, I have something, I have personal interest in something to say there too. So I'm just checking, yeah, my life is here. So I will see the comments if you commented, but first, before we start talking actually about this paper, which is 2019 paper on Hillocks, it's the little hills around Southern Alps of New Zealand. Surprise, surprise, I'm talking about this paper. I planned to talk about this paper a year and a half ago, you will not believe me. But before, I have some household things I want to discuss with you, so I'm going to just talk about this to clear the space and prepare us for these live streams. So first of all, about my channel, yes, I talk about science here, and just something to clarify, I don't talk here like about something I follow as a person. So I don't agree with everything I talk about here. So there's just some scientific facts, and you will say, how do you know it's scientific fact? I don't know. So I'm just saying what's the current science, which is published in peer-reviewed papers, and people talk about in conferences. And it could be not true what they're talking about, but that's what there currently is. People think about our world, our space, what they published papers about, and of course, most of it could be not true or not as quite as people interpreted it. And we know as a scientist that most of the stuff that we interpret, it's not actually how it is. And we talk about this in today's paper. So I don't have personal preference. I prefer this idea or this theory. I like plate tectonics, or I like flat earth theory, so here I'm just talking about what is existing. So it's nothing to do with me, my life, and my preferences. So this just clarify that, because you might see in some videos, maybe I will talk about different groups of scientists who don't agree with each other. So that's what that's the first point about that. And I also talk in a very simple language, and not just because English is my second language, but also because this channel I planned to do kind of like for children, not even children, well, students or children or people who doesn't know much about science, but they have interest. And unfortunately, a lot of science today is behind doors, so we cannot understand or know what's happening there unless you're really enthusiastic about this and have personal interest in trying to dig deeper. But otherwise, all these papers and this paper we talk today, you have to pay money, big money, to even just read it online. And of course, many people don't do it. And then nobody want to read very specific terminology papers. So that's why I'm here trying to kind of bring into YouTube world more this type of material. And of course, I have my own personal experience and interest. In particular, you can see I have a lot of videos about New Zealand geology. And it's easier for me to talk about this, and it's more interest me. And also all other topics which I said, like environmental problems or space. So you can see I have videos about how to save the whales or corals, or about some planets. Right now I'm preparing the next video about Pluto, what the New Horizons found out since 2015, so stay tuned. And I'm just myself learning so much preparing for those videos. So that's to clarify that I trying to make science available for everybody, especially for those who doesn't know anything and not interested, don't have time, and just want to know what scientists do. Next point. Yeah, and all these kind of things which I'm talking about, they kind of published in the current science community world. So I'm not responsible if something people published, it's not true actually. So please don't write me comments that I'm wrong or I support bad people, this kind of stuff. That's not what I'm doing here. You can read any theories about anything you want and take your own decision. All right, so about these live streams, we will look at some papers, and probably I will choose the papers, pick the papers which I talked about or related to my videos. So geology, basic geology principles, earth science, environmental problems, or some regional geology. For example, here we talk about regional geology in New Zealand, but it's also related to climate change and understanding the glaciers in the past and reconstructing what's happened on this planet so we can kind of predict or model what's happened in the future. So that's the main kind of point of this paper. So I will pick the papers which interested me. It doesn't have to be recently published papers, just something I'm interested in. I will use the Google Earth Pro. I have this application for a long time, and it's a very good one. It's a free one, so I don't promote it or advertise it or get paid. I don't get paid for anything, so this program is fantastic. If you want to fly around the planet, visit different places, there's a great application. You can see in 3D, you can see topography. It's fantastic for people who study Earth or like traveling, or even sometimes I use it like if I go to the part of the town I haven't been and I want to find out where the park is. Just Google and see where the parks, and you can actually go on the Earth and kind of walk the Earth and see the photographs of the buildings around you, find the shops you need, this kind of stuff. Another advantage in Google Earth, you can measure distances, elevations, you can change the light. So if we're talking about topography, geology, it's quite useful. And we also can calculate distances, I said this, and we also can look into the past. So we can look through time, how something changed, developed. If you're very interested, you can go to some cities, for example, where you live, and see how your neighborhood changed in the last 20 years. It's very fascinating. I will look in the questions you have. So far there's nothing. But I will answer them at the end, preferably. And also I will, if there will be no questions, for example, tonight, I will talk about some questions I usually have on my comments section, which sometimes I don't have time to answer. So I will a little bit address them there. What else? I say that I will choose the paper that related to my topics. I'll put the time codes after it, and I will publish this video as a video. I need to say some disclaimers. So this is live. So whatever happened here. Understand that this is not recorded, pre-recorded, and cleaned up video. So I might have speech problems, say some words incorrectly. I might swallow or yawn, this kind of stuff. So please, or I might say a lot. So be kind. I'm not a professional speaker or anything related to artistic world or performing. I'm just nerdy side. So my speech won't be perfect. Be aware. So that's all the points I want to talk about in the beginning, and now we can look at the paper. So this paper is published in 2019, and it's kind of based on the previously published paper. I know this because I know that site and I know the authors, and we talked about this, and I was interested to put this paper out for some time. Actually, I did visit this site as well, study site, several times. It's a fascinating place. And when you're there on the ground, you actually have totally different feeling. So I'll just check my sound if it's still going. Yeah. So let's have a look on the paper itself. So here on the main my picture, you can see I just took a picture of the area and these little hills, whether you see the fences going through. This is what we will talk about, this deposit. Deposit, it's just the material that's been brought into the valley. This paper was published in Journal of Quaternary Science, and I'm quite sure this paper, if you want to read it, you have to pay something like $30 or something like that. So they will give you the abstract in modern journals. Majority of the modern scientific journals will give you abstracts, some pictures, maybe conclusions, but they're not going to give you like whole paper. And especially like usually people have supplementary material where they put some data, actual samples, information, this kind of stuff. So all of that, if you're at university or student, or you have access or have friend who at university, they can get this paper for you. Otherwise, you can ask authors, and they're usually very happy to email you the copy. But otherwise, you have to pay for it. So that's another kind of limitation of the science, I think, today. So people cannot actually read the papers and see what's going on. I got this paper from a friend, so I didn't have problem. But also there's some journals, scientific journals, that start putting everything for free online, and I think that's the future, so quite happy about that. So let's have a look on the paper itself. It's quite a big paper. I read it only once, just before today, before my live stream. So just open it here. Here you can see it now. So there's 4 authors, and Samuel McCall is the main one, as I know, and he'd been working before on the site. In 2011, as I understand, he published the previous paper as part of his PhD about the site. So the idea is the Hillocks, it's this hilly site, and it's related to my video when I talk about Kyrgyzstan, if you watched my Hillock moraine video. And actually I need to finish that as well, and I will make it as a live stream as well, because it's quite complicated to do a separate video. So here, similar situation, we have these hills. That's why they're called hillocks. You can see here red dots. It's all these dot hills spread. It's not the sheep walking around New Zealand. There's a sheep too, but this is the hills, and you can see here on top of map. I think it's a LiDAR map scan, a little bit better. But when you're on the side, you can see there's a people for scale, and you can see these hills. So that's how it actually look like. It's not that quite straightforward in the field, but you definitely know there's some kind of hills, and nobody knows where they come from. So that's the site, and traditionally we have the idea that this is the glacial deposit. So back in the day, in this big valley, I will just show on this map, it was preoccupied. You see the Dart Glacier, it's the catchment of this river, which flows into the Lake Wakatipu, which is the famous New Zealand lake. And if you ever been tourist South Island, you probably traveled to Queenstown. It's located here, and this is place been in the movie of Lord of the Rings as well. So I have to mention this because I'm a big fan of Lord of the Rings. And when I watch these movies, I'm just, oh, this is this site and this is these deposits. So that's how I watch Lord of the Rings. So anyway, there's a chunk of the videos filmed in this area. I think they kind of filmed it just here, just south of Queenstown. And remarkable, so it's the slopes, big hills, big mountains they on in the video, in the movie as well. So that's the lake, and it's past glacial lake. So there used to be ice back in the day when it was ice age on our planet, and the poor people in Europe, like Neanderthals and Cro-Magnons, were fighting for existence with the ice, which constantly froze everything. In New Zealand, there was a glaciers too. You will not believe this, but it happened, and it's a very good site. New Zealand, actually, in general, very good place to study glaciology, glaciers of the past, and compare it to Northern Hemisphere, because Northern Hemisphere we have so many sites, but in Southern Hemisphere there's more ocean and less land, so it's a little bit tricky to find any evidence. So that's the valley, and the ice was, now it's just there on top. You see those blue things? It's where today's glaciers preserved. But in the past, the ice was here all over, through the lake till here, till the Kingstown, I think it's called, south. So the moraines, and we'll have a look on the Google Earth, preserved here, the terminal, the final kind of end point moraines of the ice that was sitting here in the last glacial maximum. I talk about this in my videos about last glacial maximum. You can have a look. So it was a big ice, and then in the last 20,000 years it's melted away slowly. And why it was melting away, it's plugged out this how called trough, like a deep depression in the mountain between two big slopes where the ice was sitting. And when it was retreating, there was a lot of water and rocks coming out of it and washing everything, melting everything, and it's left that lake because it also was a lot of water which ice melted, and it's not, you can see, not very easy access to the ocean to drain. So the deep trough accumulated a lot of water, and it's still supplied by all these little glaciers in the valley, not as much as during the retreat, but that's the reason of creation and existence of the lake here now. And we have this site here. It's kind of just getting up in a wider area of this valley, away from the modern shore of the lake. You guys can see my no, you cannot. Yeah, you can see my button. That's good. My mouse. So here there's the deposits, and traditionally, here, Mount Alfred, and between Mount Alfred, traditionally this deposit was considered to be the way, the point where the glacier kind of stayed for some time and created this deposit. So people thinking this is definitely rocks and material that have been brought by ice back in the day, whatever 1,000 years before present, and then the glacier melted. And you can see the river going through here, so it's been rewashed a lot, and we don't have much preserved. Like everything in this valley, whatever was preserved during the glacier retreat, been washed away or destroyed by the very, very active rivers. In New Zealand, very active rivers. And they carry a lot of rocks. And they're quite active, especially in times of when there's a lot of rain. So they can flooded everything, demolished everything, and then on a good day it's very lovely. So you will never even know about this. So rivers doing this thousands of years in demolishing everything. So we're very sparse on any glacial deposits here. So that's what the paper gonna look at. And so traditionally people thinking this is the glacial stuff, we can date it and we can tell when the last time glacier was here. But the new research come out and the people talking about, no, it could be not come from the glacier, it could come from the slope and form the landslide. And I'm talking about this before, and actually my research was related to that too in my previous video and discussion as well. So you can go back and check it out. So let's have a look on the abstract. So the ambiguous landscape histories, so these reconstructions or interpretations which might be not true, can arise from incomplete geomorphological, sedimentological, and geochronological evidence. And that's the main sentence which summarizes all the paper. So if you have some kind of suggestion about a region or formation of particular hill or slope, all your idea of what's happening in a valley, in a country, or even geology, historical time in that area could be wrong. So here we see they're proposing analysis to robustly assess the origin and age of a field of rounded mounds. They're called mounds, hills, hillocks, known as hillocks. We're using cluster analysis, sediment. It's consistent with landslide origin, but inconsistent with other glacial sediments in the region. So the very outsiders there, these hills, whatever material within, it doesn't match anything surrounding, and that's kind of question mark. Cosmogenic beryllium 10, so this is the dating technique we use. Cosmogenic, it's mean the air radiation that come from the space, this kind of background radiation, not from the sun, but background in the space. There's a lot of radiation. It could be detected, and it's coming onto the Earth, and whatever this on the surface, being bombarded with this. And beryllium, which we can find in quartz material in the rocks, will be decay because of that, because of this radiation, and we can pick it up in a lab and figure out how old this rock by knowing when this quartz particle start being exposed to the space. So when it's come out on the surface. For example, if you had ice, when ice melted, that will be the time when this rock quartz start being exposed to the space. Yeah. So if my dates tell me 6,000 years, so 6,000 years ago, last time this rock been covered. Doesn't matter landslide or glacier or somebody was just covered it. They use also, they find out that it's about 8,000 years. The penetrating radar reveals the deposit rest upon deltaic forested beds. And I just lost my line. And and with topographical data they calculated the volume of these deposits about from 15 to 27 million cubic meters. And that's kind of nicely matching with what they suggested, because they proposed the source area in the mountains where it's actually come from as well. So they're indicating that a region of rock avalanche deposits, and it's about 8,000 years old. And at that time, the level of Lake Wakatipu, so the level, as I told you, will depend on this ice melted, and the water level in the lake actually will be changing. Depends how much water going into. And the lake was lower, 340 meters by that time. And they're talking about the shoreline, so that's the basically summary. These findings are significant given the lack of landforms by which to constrain glacial or post-glacial landscape histories in this region of New Zealand. So in New Zealand, in some places we have a lot of good deposits, and some places not, and people drawing conclusions from the suggestions. So have a look. Let's have a look on the Google Earth where it's located. The New Zealand, nicely located in the middle of the ocean. Actually, it's located between two oceans, Pacific and the part of the Indian Ocean. Yeah. Okay, I hope the live's still going. Oh no, I didn't switch. Yeah, that's what I didn't do. little meandering around. So that's the New Zealand and Pacific, and this the Tasman Sea, which is supposedly the part of the Indian Ocean. And we're talking about South Island, and we're going into this area, kind of south central part of the South Island, where the Wakatipu Lake is, and it's a little bit crooked like that. Most of the lakes going straight down to the south, but that one a little bit twisted. There's more complicated geology in that area, if you can see. I talk about a lot about geology of Southern Alps in my previous videos. You can have a look in history of formation. We talk about Castle Hill Basin in specific, talk about schists and rocks and mountain formation. So I have good videos about that. I can send you there. But you can see here briefly, if you don't want to watch those videos, there's a fault coming through. It's quite straightforward. You can see it from the space, I believe. I haven't been in space, but probably you can. And if you look closely, look, it's a very straightforward line. And the highest mountain peaks a little bit east from there. I don't know, maybe 20 kilometers or so, but that's the highest peak. The Mount Cook is here. I talk about this a lot when I talk about glaciers, all the lakes of the glaciers, and about geology. I love this area in particular. And we have a lot of valleys, and further south we're going to this Wakatipu. So you see those actually glaciers which preserved, they closer to the Alpine fault, and they were fed by this highest peak of Southern Alps, similar like Mount Cook region. And then we have these two kind of big valleys feeding the Wakatipu. That's the Queenstown, party town. Well, it's not party town, but people go in there, especially in the winter. They ski in there. People go there in the summer, do a lot of jet boats and this kind of stuff. So it's very popular. There's a big airport, you can see here. And this nice peninsula, I think there's a golf course, and even that's where they filmed Lord of the Rings, I have to say that. And we have the Arrow Valley. It's a little bit kind of up the stream. You probably will travel here if you're going to the west coast through here, but usually people take different routes. Glenore here, it's somewhere there, and I turned off all the names, so otherwise be too busy, but I preserved the pictures and we'll have a look. So that's the shore of the Lake Wakatipu, Kinloch. Wow, it's a good image. And yeah, by the way, this is all copyright probably, so don't take offense. I'm using it because it's for free in Google Earth. You put it there. They say Isengard Lookout. That's probably been in the movie too. And we see this very braided river called Dart River. Very nice, interesting name. Already clicked this. Yeah, and it's very plain. You can see there's not much. So this is all river deposits which have been reworked by the river since glaciations, top of the mountains. A lot of farms, people use it, farming. This second river join in. I forgot the name, so I'm not gonna put it. Stables, okay, very lovely. And then we have these hills, and even from this image you can see they're there. But one thing that will strike you the most, look at the river. So it's going from the north nicely, taking quite wide extent. So it's going from shore to shore. It used to be here, but then it's been diverted. You see this, now there's like a little lake, I believe, Diamond Lake, yeah. So there used to be a stream going through, and then something happened, it's changed the catchment, but the water stayed there. So it's very common in New Zealand, especially around Southern Alps. There's a big bedrock, Mount Alfred. Oh, there's an amazing view from top of that, and this is actually a view on the hills I'm going to talk about. So this, somebody standing on top taking photographs. That's the bridge going through, and these people see this there. So if you're going there, you're going to drive through this bridge, and you see those hills, yeah. So you might see, oh, it's something normal if you're not geologist, but the geologist will straight away thinking, oh, where it's come from? Because look, everything is here is flat and reworked by the river, and you see the river here almost taken from shore to mountain to mountain. That used to be old river as well, passage, and you see there's a little swamps leftovers, and then people of course regulated at all now. Yeah. So here river brought a lot of material here, and she kind of spread into two directions. But this is for fluvial people. They love this kind of stuff. But look at the river, what I want to say. Yeah, that's the view. Very beautiful blue water. You have braided, and it looks like it might go through, just straight through. And it will, probably. Would, I would say. But something happened, and you have a lot of material here. And the poor river have to redivert, change its course, and go around it. And you see she went all the way till the opposite slope and back to the middle, of this valley. And this valley not very wide, and if you can imagine, I love the Google Earth. It doesn't show you, unfortunately, but I have the ruler. I don't know why it doesn't do this. It doesn't do on a live stream or recording. Maybe it's the OBS Studio. So I put the ruler from road on the left side to the right side, and it showed me 1.6 kilometers. So it's not very wide area, and that's what's happened. So scientists suggested this is the landslide. So the slope collapsed, and we probably can have a look where from here down. It's a little bit exaggerated, my topography here, for better perspective, but you can imagine. And it's fall down here, and it's blocked the river for some time, and then she went through here. And on this picture, which we've seen before, you can see it when it's kind of wind around some slope. So here maybe we see the source. Probably it's there. So lovely. So that's the settings, and we're going to talk about this lake, how it's affected it. And in the past there was all ice, as I told you, and that's the moraine, terminal moraine, the end moraine I talked about, which the city is now on, I believe. It's not very straightforward. Sometimes these moraines could be quite tiny. Yeah, I believe it'll be somewhere here, these ridges. And it's all been dated before, and people trying to understand how it's related or same like in the northern hemisphere, like in European Alps or Scandinavian ice sheets or even North American ice sheet. And it's not just a question of that, it's also about how we interpret it, what we see in the field, how detailed we should study, things like that. That's the main point of this paper. And for you, might be not end of the world, but some scientists would spend all their life dating and writing papers. It could be quite significant when somebody say, all your work is not true. Yeah. All right, so let's come back to the paper. Let's go through. So the introduction, it's a very nice introduction. You can read it even from my live stream if you wish. Just check my sound. What's going on? So glacial chronologies, landscape histories, and hazard assessment must be underpinned by a reliable assessment of landform origin. That's just what I talked about before. So the glacial landform, it's moraines, and they're quite similar to landforms that are produced by the landslides, and that's I talked about before as well in my paper. But it could be geomorphologically similar, so like appearance is similar, but the sediment, the material could be different. And that's why people confuse them. But often people just don't even go and look on the deposits, they just map it from satellite images or something like that. Now Google Earth, they date it, they don't even look on the material itself. And often you cannot, you just go there and they're just hills. So if I go into my original image, if the river will not cut through and I see actual material, what can you tell from this? Okay, some kind of rolly hills. I don't know what it's inside. Is it the bedrock? Is it the sediment? So you have to go and investigate. Yeah. So let's come back to our paper. So there's a very nice introduction. So we should differentiate. They say in this study, we investigate the hillocks. We already know that. And we argue it's produced by rock avalanche. And apparently sounds like it's a second paper, and a little bit modified and improved with new dates. So they have new cosmogenic dates, which assess whether or not the landform H is consistent with the late glacial origin as previously assumed. And it's bring light, shed the new light on the post-glacial landscape evolution in this part of New Zealand. In New Zealand, Southern Alps very active, so there's a lot of earthquakes, and slopes quite unstable because just recently there was all glaciated, and you can see they're all steep. A lot of it there's a schist, and I talk about this in the geology of New Zealand, Southern Alps in particular. So they can imagine they're quite active, so they're falling down all the time, slopes, rocks, and the rivers modify them. And we still have this deglaciation rebounding when the rocks kind of like become free from the ice and everything that's been loaded on them, and they're relieving this stress now, and a lot of landsliding happening. But with New Zealand earthquakes, it's not a biggie. Just have a big earthquake and then couple good torrential monsoons. We have this rain season, especially last several years with La Nina, and you have a lot of landslides as a result. So regional settings, we talked about this. I'm not going to go in detail. We've beautifully done map. And in scientific papers, you usually have to describe geology. They talk about this type of the rocks that you can meet there. They talk about geology. They're talking about what's happened with the glaciation. So it's catchment that fed into been glaciated during the Quaternary period. And today's 6-kilometer long Dart Glacier sits at the head of the Dart catchment, and that's the one that I showed you on top of it. Actually, I didn't zoom in. I think this is the Dart Glacier here. Quite small now, but used to be all over in the valley. Just need to come back to my original settings. Yeah, that's better. All right, so let's come back to the paper. And yeah, they're talking about glacier erosion, Tyrian terminal moraine. This is one kind of like last LGM, last glacier maximum moraines. A moraine is just a glacial deposit, yeah. And then he talk about the level of the water in the lake, and it could be important because when you're trying to understand how much water was in a catchment, how much displacement happened, so how much ground actually rised or deepened, all these things, and the level in the lake will differ. So they're saying here, let's just read. So there's evidence represented by stranded lake shorelines, alluvial fan terracing, and delta faucets that Lake Wakatipu was previously been up to 50 meters higher than the present day. Radiocarbon dating of wood excavated from one of the shorelines cut 26 meters above the current lake level suggested the lake was at the level at about 10,000 years before today. Yeah? The highest preserved shoreline, 50 meters above the modern lake level, is suggested to have formed at least 1,000 years earlier. So little information is there. And we see some of the delta, like Wakatipu Forsets beds preserved east of the Mount Alfred at elevation 358 meter sea level. And it's about 10 meters above the modern Dart River floodplain. So that's what we have so far. So the methods, they looked in deposits, morphology, sedimentology, geophysical, and chronological tools. So they use dating, so they date the rocks. On top of these quartz, they did collect the samples and looked at the sediment. I talk about this about my research very specifically. Morphology, so they assessed where the hills can be found, how they aligned, how many of them preserve this kind of stuff, where the potential source of the landslide, and calculate is it matching the deposits or not. In geophysical, here we're talking about actually grain penetrating radar. So when you scanning through the earth, and by the differences of how the wave penetrating through, you can see with the different medium, and then you can figure out, oh, this is this material there, or there's a water or something else. Sedimentology. So this is very classical. I looked through 50 clasts they collected. Traditional among glaciologists or just geologists. We're looking on the rocks, the shape, the angularity, and we create statistics, and then we see if these rocks more look like glacial or come from river or from the slope, this kind of stuff. So we'll talk about this here. We looked at a picture of the results. Age assessment, so they took the data boulders. They have some from accumulation area, so where the actually rock avalanche come from. They have some on the way and from the fence they've been creating since, so they have a little bit like backup plan. So they didn't just data the hills, but other material around it. And they say you can read in specifically in detail where they analyze the samples, how, and it's pretty standard for this. So they took samples, crushed the rock. You do crush the rock, separate them, and then there's a lot of chemical washing going on. It takes several days, and then when you took this beryllium out, you take to the accelerator mass spectrometer. We have one here in New Zealand, GNS Science. There's one in Australia as well, and it gives you the date, approximate date. That's the beautiful site. So this the rocks that they dated. So they're looking for these quartz veins within, if you can see. And then they estimate how the slopes, for example, this rock exposed to the slope, to the space, and when it's morning or evening or whatever, it's shadowed by the slopes. And then they estimate for our latitude, how far we're from equator, or this kind of stuff. So how we exposed to the space. And there's a standard procedure, so you use some kind of methods or develop your own. Subsurface investigation, it's the grain penetrating radar, or GPR we call it. It's quite complicated. Well, it's not complicated, but it's heavy and time-consuming thing. So you go there and actually do these measurements. But it gives you a beautiful image, and we can have a look here. So I don't have to talk about this. It looks like that. So this is just a wave. So this line on top, it's kind of air between radar antenna and the ground, and then you start seeing surface. So these kind of waves show you different angle, different material. And something will, the wave gonna go through faster, something fine or wet or something like that. And then if you have big boulder or heavier material, different strata, for example, if you have sediment and underneath you have bedrock, solid rock, so there'll be, you see the border, the difference. And that's what they're showing in this image. You can have a look in detail and read the description. And it's actually give them information how deep it is and how far it goes. We talk in detail of what they use for that, which methods, and programs. And the volume and morphometry of the deposit. So they get nice, created nice images. They use the aerial LiDAR, kind of scanning through so you can see the topography without vegetation. Modern days you can do it with a good drone. You just fly it over the area, but it's all equipment, money, and time, and you need to know what you're doing. So they assessed everything, built the map, and then they will see in the results section what they estimated. So results, sedimentology. So pretty much they write down this angular class, supported, poorly sorted, and lag bedding structure. So it's very typical for a landslide. We actually, let's have a look on the pictures here. This is how it looked like. So it's one of the hills cut through, and you can see the very different class. You have bigger things in between, smaller, and very angular, and you can see it's same lithology. Even here, without without looking at actual material, we can see that it's all similar, same actually lithology. If it was glacial, it would be everything represented that in a catchment. So there will be rocks. They'll be more sorted, so it'll be more rounded and kind of more aligned rather than like that. And they will have a different color, for example, like sandstones, mudstones, a little bit of quartz or something else, or volcanic rocks, everything be more aligned. And there's a lot of fine metrics, which is very important when you have a big landslide. So here we can see the We can see the results of the sediment. Hillocks, it's quite angular, poorly sorted. And you can see it's very nicely matching to not even glacial, not even close to the glacial, sorted, rounded, and kind of sieved through with the water, a lot of water mixing substratum. So now these ones are quite not that not that sorted. So it's quite straightforward that it's come from something else. For example, one event, rock avalanche. They're talking about dating, so the dating, not going to the date, but the age assessment, correct name for that. And I talk about a little bit about dating techniques. I want to make a bigger video about cosmogenics. Oh no, I don't want to do this. Cosmogenics, and they use beryllium. So you can, if you're interested, write me comments. Yes, we want a video about that. And here, if you learn more, you will be easy understand what they're talking about it here. So we will read in results and subsurface information. So they did this GPR, as I say, and calculated approximately the size of the deposits. And this is interesting. This is your dating result. So they also did the Schmidt-Hammer. Schmidt-Hammer, it's so interesting. It's the German interesting system that people start using. You know, the people using Schmidt-Hammers to test it if you're, for example, you have a metal surface or, I don't know, sheet of metal or something, you want to build buildings or use it in industry. And the Schmidt-Hammer is little like gun equipment. You shoot it through the surface and it shows you how weathered or how weak the surface is, how it's going to be exposed, how it's going to be deteriorate fast or not, how resistant it is. That's what it is. It's very simple, kind of mechanical. It's just shoot it through and it show you the gradient, the number. And people start using it in geology, so they go on the rocks and they smash them with the Schmidt-Hammer. Well, it's not actually smashing, you just point it and you press the button. And they give you the reading. And if you go through one deposit, it should everywhere show the same reading. And if something different, it will be all different lithology of that rock. It's mean, for example, some rocks more harder and they preserve longer, some more loose and they'll have different readings. But it also means that this rock might be from something else, so, and been here older and been lying in the valley all longer and been exposed to erosion and have a weaker surface. So they did Schmidt-Hammer. I didn't know, it's kind of funny. And then they did exposure age as well here. And they show this, the mount is actually this hill, so the one hill, second hill. So it's all kind of within debris fan, a little bit younger, which obvious, it will be younger than the deposit. Deposits first happen and then the debris fan built. And we have the source area kind of matching with the hills. So, and it's all about 7.88 thousand years ago. You see, it's quite a big difference, but it's also the method, how we calculate it, it's so complicated. So there's so many factors included. So if we have about plus minus 1,000 years, it's good enough, isn't it? The more we go into the past in the science, the more we're talking about these kind of things. We're talking about thousands and millions of years, plus minus. In the modern days, we will talk about months and days, even seconds and minutes. So that's the difference of our time perception. It's also how hard it's to go into the past and exactly know what's happening. Unless somebody put the watch into these deposits when it's happened, with the date and time, we'll never find out exact date. So we talk about the volume, they estimated it. There's a very nice info about elevation of each of the hill, how it's aligned, a very detailed work. And they have a discussion about the origin. So let's see how much time we have. I wouldn't have much time. I don't have much questions. I don't have any questions. Nobody watching me because I didn't announce myself. So let's just go through discussion. So they speculate, of course, that it's landslide origin. Where did you say that? Volume and source. So they suggested quite a big volume, and it's quite typical for this landslide that can happen. And it's kind of matching our source. So that's the alignment of the hills. That's the profile topography from T to T, so one direction and perpendicular. Implication for landscape development chronology, that's what we need to look at. So they're saying that the Hillocks is a landslide deposit, has implication for understanding glacial and post-glacial landscape change in this region. First of all, it'll tell us that it's not glacial deposit. Hello. So we don't know if the glacier was there at that time or not. Another thing, that the landslide happened 8,000 years ago, so it's mean the ice was already away from there, because we still have it there. If there was ice, it'll be reworked or moved away. That's another good implication, yeah. I don't know if it says here. It should. Yes, provide some constraint on prehistoric timing positions of the Dart River Delta and the level of Lake Wakatipu. I think they're more focusing on the level lake water level. And I think because the author's involved in some other work about this level and shores and terraces and the lake, so that's why they kind of emphasize it here. So we have a constraint on the maximum delta progradation rates of 1 kilometer per 1,000 year, and average since 8,000 years ago. They also say about surface and abandonment may relate to a blockage of that river by the rock avalanche, which we talked in the beginning, possibly driving temporary ponding and degradation upstream. And we can see this, can we? We can see this on the Google Earth. That's what I talked about when we have this kind of like, that's the temporal blockage. But I think this probably won't be related to the landslide. Although it could be that it's blocked it and then the rivers find a way through here before it's cut through. It could be. But I think that one related for previous, when the ice was here in the area. We have this interesting lake here as well, and the way how the river developed, you know, upstream. So that's what they're saying here. Maybe you don't need it in such a detail, which I've talked about, but we're going through the paper, why not? So let's have conclusions. What have the conclusions? That's a very important part of your paper. You can read abstract and conclusions. You'll be quite sweet if you don't have time to read through all the paper. And only when you start analyzing something specifically, you will go through every word and details for the paper. If you're working on the site, if you cannot find some information. So scientific paper could be versatile. You can use it for different things. You can just read the titles and make your conclusions, or you can go in detail as much as you can and make your conclusions. So the information of morphology, sedimentology in this study favor rock avalanche region. We know that. The class morphologies within hillocks are consistent with rock avalanche deposits, but not with other proposed deposits or mechanisms. The morphology and distribution of the mound suggests thinning of the deposit and reduction in mound size in a cross-valley direction away from the proposed source area, and that's normal for landslide. That's why they build those profiles to see. The most plausible source area identified for the landslide seems to be the basin to the west, which has a scar with a volume compatible with the volume measured by for the hillocks. And it has produced boulders with the lithology matching that of the hillocks. So the rocks, the source volume and geology matching what we found downstairs, yeah, down the valley. So that's what they're saying, and that's why they did such a detailed work there. If you wonder, GPR data indicate that the deposit was emplaced upon a braid plain and prograded delta. So it tells us there was no ice already in the valley when this happened. So it just went down over the river material. And our dating, beryllium 10 exposure day age, give us about 7.9 thousand for the mounds, and statistically indistinguishable ages for adjacent landform assumed to be related, provided further support for rock avalanche region. Yeah, that's it. Basically, it's confirmed that. But it's nice to have a date now. And indicate a Holocene timing for that event. So 8,000 years ago, I have a video about Holocene. You can see what's happened in Europe at that time, and there was a Dart landslide happened in New Zealand. Hopefully nobody has suffered that time when it's happened. Nobody was covered. What else they say? The new data that 8,000 former Wakatipu glacier had certainly related up valley past this location, and the Dart River had prograded down valley of this location, providing useful constraints on glacial and post-glacial chronologies in the otherwise fragmentary record of events in this catchment. Furthermore, this study demonstrates the utility of quantitative methods of landform identification and analysis for informing studies that utilize landforms for paleoclimate or landscape reconstruction. So that's one of the points of this paper, that we can detailed look in these deposits from all aspects, and dating, and where it's come from, and morphology, and lithology, and GPR, and how it's related to what's happening around it. And only then we can draw conclusion about climate change or what's happened with the glaciers in this area. And there's a very good list of reference which are important and used in this paper. So that's the paper, and I'll finish now for that. And I will see if there's any question. There's somebody watching me, so if you have any questions, I'm in the chat. Maybe I don't see it. Maybe you ask me a question, but I just don't see them. I just look on my computer. No, I don't have any questions. So if you don't have question, I had one question I wanted to address at the end. Maybe it'll be interesting for you. So we're almost an hour, so just wait till it's 1 hour and we go offline. So the question I have quite commonly, I don't know if you noticed, I don't actually have a chance to read all the comments, because some comments, the new comment I can see on my little program, but when people ask me that question as a reply for somebody's question, I have to go specifically into this video and look through, so usually I don't see that. But sometimes I go there and actually accidentally see that there's a whole conversations there, and people say like that I'm not like a real person, so that's very shocking for me. I don't know, maybe this is happening with many people on YouTube these days who doesn't show themselves, but I assure you that I'm a really real person. So, and you can see I'm breathing, sneezing, swallow, so I am a real person, and I'm not artificial intelligence or anything like that. Maybe the way when I record my videos and then I edited them, so I put away like in between my sound, I make it quiet, this kind of stuff, and I put music. Maybe it sounds like I'm fake, I'm not a real person, but I'm very real, because you can hear it from my videos that I'm not reading the text like right now. I'm talking from my mind, so I never, in my videos, I read like text. Maybe I read like a sentence from somewhere, but not a text. And I don't prepare any text when I do my videos. So, and I only record them once, so I never done like, oh, I didn't like how I say that, and I'm gonna re-record it. No, I don't have time for this, because I do it in my spare free time, which these days I don't have at all. And often it's like late night, I just sit there, record it. And I just use my belief that my mind will say what it's supposed to say. So I do research if it's unfamiliar topic, for example, about Pluto right now. I didn't know actually all interesting information we learned since New Horizons arrived to the Pluto system. So I'm talking about this right now in the next video, and you will see that I do research. So I have like a little plan. Sometimes I save images I want to show, and then I talk through that. But I don't read any text. I don't prepare any text. So I don't know where people take it from that I'm artificial intelligence. Unfortunately, I'm not. So that's the interesting question which I have often. That I'm not actually real. Some other questions I have often, unfortunately, not many of them related to the science. So I'm just like discard them, I don't read them or don't pay attention to them. But if you have any questions about this particular paper and want to do discussion, I'll be happy. And my next stream, probably will be in a couple of weeks or so, but some other paper. Maybe I will not know as much about that paper because I will not off. This is a particular case because I've been on the site and I can talk about New Zealand a lot, but maybe some other papers from unfamiliar site we can just go through together and it will be maybe faster. So now we're 1 hour live. I will leave this video as it is on the live section and I will cut away about the paper and I put it as a separate video. And I put the time codes. So thank you so much for joining me today, and like it, subscribe, share it, and I will see you in my next videos. Have a lovely week, day, whatever you do right now.